In this lecture, I'm going to state and prove the celebrated Polya Enumeration Theorem. So before we get to the statement of the theorem, let me try to explain what the problem that it addresses is. So recall that when we have a finite set U, we can talk about permutation groups. These are subsets of perm U, that is permutations on U, which are closed under composition and inverse. So let's say G is a permutation group. And we also choose a number K, and we say K, the set of integers 1 to K, we think of that as a set of K colors. Okay, so a coloring of U is just a function C from U to K. So for each element of U, you assign a color, one of the K colors that are provided to you. And well, that's not much of a definition. The definition really is of equivalence of colorings. So two colorings, C and C prime, are said to be equivalent. Well, I should say G equivalent. It depends on the permutation group that you've chosen. If there exists a permutation sigma in G such that, so the color assigned by the coloring C prime to G sigma of U is equal to the color assigned by C to U. Okay, so let me just define some notation here. So we'll say CKU to be the set of all K colorings of U. I'll say C is equivalent to C prime under G if C and C prime are G equivalent, and we'll use the notation G mod CKU to denote the set of orbits, set of equivalence classes of K colorings. This is really consistent with our earlier notation for orbit spaces, because you can also regard G as a permutation group of not the set U but the set of K colorings of U. Okay, so the object of Polya's enumeration theorem is to give you a method to compute this number of orbits, but in fact a more refined counting, as I'll explain in a moment. But before that, let me just give you an example, and one which we've seen earlier. Let's take U to be the set of integers from 1 to n, and let's take sigma to be the permutation, which is just an n cycle. So 1 goes to 2, 2 goes to 3, 3 goes to n, and n goes to 1. So I denote it in this notation, but really what it is in one line notation, it is it is given by 2, 3, n, 1 in one line notation, and its directed graph looks like this: 1 goes to 2, goes to 3, goes to ... goes to n minus 1, goes to n, goes to 1. So it really looks like a cycle, and we'll take G to be the group generated by sigma. This group consists of all powers of sigma and also the identity. The order of sigma, you can easily see, is n. So G equivariant K colorings are nothing but necklaces. Sorry, G equivalent of K colorings is nothing but equivalence of necklaces with n beads each having one of K possible colors. We encountered this counting problem before as the problem of counting the number of words in an alphabet with K colors and of length n up to conjugacy class, up to conjugation, the number of conjugate classes of words of length n in an alphabet with K letters. It's the same problem exactly. Okay, so now let me introduce to you the refinement of the counting problem. So not only do we want to count equivalence classes of colorings, we want to count colorings where we specify the number of elements with any given color. So to write this nicely, given C belong to CKU, let alpha I be the number of U in U such that C of U is I. So it's a number of elements of U that are given the ith color, and this you can do for I goes from 1 to K for each of the colors. Now I can write down this vector alpha subscript C, which I will define to be alpha 1, alpha 2, alpha K. So this is a vector, each coordinate is a non-negative integer and has K coordinates, and moreover note that alpha 1 plus alpha K is going to be the total number of elements in U. And this we call the shape of alpha, of C. The shape of the coloring C. And one thing that's obvious is that if C is equivalent to C prime, then let's say G equivalent for any group G, then of course alpha of C is equal to alpha of C prime, because the colors assigned to an element U is the same as the by C prime to an element GU is the same as the color assigned by C to an element U. All you're doing is you're moving around the points but assigning the same number of points the same color. So yeah, so now here's the refined counting for each alpha in n raised to k with let's write this, let's call this the size of alpha. So if alpha equals alpha 1 alpha k, we'll use absolute value of alpha to refer to alpha 1 plus alpha k. So with size of alpha equal to the size of U, let C alpha U, so this is only some, this is the set of colorings of shape U. Shape alpha. And the problem is the following: determine the number of G equivalence classes of colorings of shape alpha. When I specify alpha, it's presumed that I have specified, alpha is a vector with k coordinates. I've also specified the number of colors. And the Polya Enumeration Theorem gives a solution to this problem in the spirit of the orbit counting theorem that we had looked at in the last lecture. We are almost ready to state the Polya Enumeration Theorem. I just need to introduce a little bit of notation from the theory of symmetric functions. So these are the power sum symmetric functions. Or rather symmetric polynomials. So recall that a polynomial in variables, so a polynomial f of x1, xk in k variables is said to be symmetric if f of x1 up to xk, you can rearrange the variables anyhow you like, is equal to f of x omega 1 x omega k, where omega is any element of perm k, any permutation of the set 1 to k. So an obvious example of this is the polynomial Pm of x1, x2, xk defined by x1 to the power m plus xk to the power m. So it's just a sum of mth powers of k. So this is called the mth power sum symmetric function. Or a symmetric polynomial, I should say. I'm using the word function, but really they are polynomials. Okay. And in general, given a partition mu, we can define a power sum symmetric polynomial corresponding to the partition mu. Given an integer partition mu, let's say mu has parts mu1, mu2, mu_m. Let p mu x1, xk be the product I goes from 1 to m, p mu I. Okay, in other words, I'm just saying x1 raised to mu1 plus xk raised to mu1 into x1 raised to mu2 plus xk raised to mu2 and so on all the way up to x1 raised to mu_m plus xk raised to mu_m. These are also called power sum symmetric polynomials associated to partitions. And one more thing, a small piece of notation I should introduce so that I can state the Polya enumeration theorem easily is now given sigma in per mu, I'll define mu sigma to be the cycle type of sigma. So this is going to be mu1, mu2, mu_m, where mu1, mu2 are the sizes of the cycles of sigma, written in weakly decreasing order, though it doesn't really matter what order you write them in for the purposes of this definition. And what we'll be doing is, to a permutation sigma, we'll be associating the polynomial p sigma mu in the Polya enumeration theorem. So let me state the theorem now. So as before, let U be a finite set and G be a permutation group. Then the sum over all vectors alpha with alpha 1 plus alpha k equal to size of mu. So alpha 1 alpha k in n raised to k. So the sum over all possible shapes of the number of equivalence classes of C alpha u by G, and then I'll write x to the power alpha. Now here maybe I should have introduced this earlier. Given shape alpha, I will denote alpha is alpha 1 up to alpha k. I will denote x by x to the alpha, the monomial x1 raised to alpha 1, xk raised to alpha k. And so that's what it is here, x to the power alpha. So now if you know this, so this is a polynomial in k variables, and in fact it's not very difficult to convince yourself that this would be a symmetric polynomial. And if you were able to compute this polynomial somehow, then you would be able to count the number of equivalence classes of colorings, of G equivalent colorings of any given shape. And so the right hand side of this equation is going to give us a very simple formula for this polynomial, for this symmetric polynomial, in terms of symmetric functions, power sum symmetric functions, and it looks very much like the orbit counting theorem. So it is sum, and then there's again a sum over sigma in G, average so to speak, but the summand is surprising. It's P mu sigma of x1, x2, xk. Okay, so in principle it's very simple if you really understand the cycle type of the elements of G. And let me give you a proof now. The proof is, well, there's one step which is clever, but it's basically an application of the orbit counting theorem. So by the orbit counting theorem, what we have is this thing. So this is amenable to the orbit counting theorem. The number of orbits C alpha mod G is equal to 1 over cardinality G summation sigma in G, and then you just have to count C alpha u sigma, the sigma invariance of C alpha u. I mean, as I was saying, although we started with G being a group of permutations of U, you can also think of it as a group of permutations of C alpha U. And so the orbit counting theorem applies there too. And now we need to somehow take this thing on the right hand side and show that it is in fact what appears on the right hand side of the Polya enumeration theorem. So that's a lemma, and so the lemma is that summation over, okay, of course not just this thing, but we are actually summing over all alpha. So alpha 1 plus alpha k equal to U, we're looking at alpha 1 alpha k belongs to n to the power k. C alpha U sigma x to the power alpha is p mu sigma x1 x k. So here we have fixed sigma and we are varying alpha. Whereas here we had just fixed alpha and we are varying sigma. Okay, the idea behind this lemma is that a sigma invariant, if you have to have a coloring that is sigma invariant, then all the elements in a given cycle of sigma better have the same color. In fact, if all the elements in any cycle of sigma have the same color, you can keep applying sigma, and since you'll be moving within the cycle, the coloring will actually be sigma invariant. So the point is that, so this is the proof of the lemma. And of course, once you've proved the lemma, it's easy to see that you've proved the Polya Enumeration Theorem. A sigma invariant coloring is a coloring of cycles. Coloring of U is a coloring of cycles of U. So now let's just look at the right hand side here. What does this look like? So P mu sigma of x1 up to xk, well, by definition this is the product. I goes from 1 to m. Let's say that mu sigma is mu1 up to mu m. So then this is the product. I goes from 1 to m, x1 raised to mu1 plus xk raised to mu k. Sorry, this is mu I, xk raised to mu I. Now using the distributivity law, this is equal to summation j1 goes from 1 to so I'm going to just take these sums out and put the product inside. So j1 goes from 1 to k, j2 goes from 1 to k, all the way up to jk goes from 1 to k, and then I have to take x1 xj1 raised to mu 1, xj2 raised to mu 2, x not j, this is jm goes from 1 to k, xjm goes to the power mu m. Okay, that's just distributivity of multiplication over addition. And now you can think of this as a sum over j1, j2, jm in k raised to m. Okay, and then we have xj1 raised to mu1, xjm raised to mu m. Now each vector here, each j1, jm, so each term in the sum determines a g invariant coloring of U as follows. Color all the elements of U in the jth cycle in not the jth cycle, in the ith cycle, that means the cycle of size mu I. So sigma has cycle type mu1, mu2, mu1. So it has, we'll call the cycle of size mu1 the first cycle, the cycle of size mu2 the second cycle, and so on. Let's just fix an ordering on the cycles. And you color the elements in the ith cycle, which is of size mu I, the color ji. Okay, then if this coloring has shape alpha, then what we must have is that xj1 raised to mu1 xjm raised to mu-m is going to be x raised to alpha, because this coloring of the ith cycle will give you, if I choose the coloring color ji for all the elements of the ith cycle, there will be mu I elements of that color, and so we would have to write xji to the power mu I for that. And so totally the number of elements, this x to the alpha will actually just be the shape of the resulting coloring. Moreover, every sigma invariant coloring arises in this manner. Every sigma invariant coloring is just obtained by choosing a color for each cycle of sigma. And so this sum, this thing on the right hand side, is nothing but the weighted sum of all sigma invariant colorings of shape. It's just the weighted sum of all sigma invariant colorings of U, weighted by, if it's of shape alpha, then the weight is x to the power alpha. And so this proves the lemma. And now the Polya enumeration theorem is easy. What we get is G mod C alpha U summation alpha x to the power alpha is equal to, and so we've already seen that it is 1 over G summation sigma in G C alpha sigma. So there's a double summation here. And I should say sigma in G, and what do we have? We have here C alpha sigma and we have x to the power alpha. But this is nothing but 1 over G, and by the lemma this is nothing but sum over sigma in G, reversing the order of summation, P mu sigma x1 up to xk. And that is concludes the proof of the Polya enumeration theorem. Let me show you how easy it is to actually compute these things. Let's take an example where we take n equals 4. So U is just the set of elements 1, 2, 3, 4. Sigma is the 4 cycle. So an example of the necklace problem. And so let's look at the group G to be the cyclic group generated by sigma. So this has 4 elements, the identity of 4. It has the element sigma itself, which is 1, 2, 3, 4. Then it has the element sigma squared, which takes 1 to 3, 3 to 1, 2 to 4, and 4 to 2. So it has 2 cycles, 1, 3, and 2, 4. So let's write it like that. Then it has sigma cubed, which is nothing but the inverse of sigma. It has again just 1 cycle, and that takes 4 to 3, 3 to 2, 2 to 1, 1 to 4. So these are the 4 elements, and so it's just going to be a sum with 4 terms. So what we get is that summation 1 over G sigma in G P mu G x1. Let's do it with 4 variables. So we are assuming that there are 4 possible colors, and this is going to be just 1 over 4. So we'll take first the term corresponding to the identity. So the identity has cycle type 1, 1, 1, 1. So we have just x1 plus x2 plus x3 plus x4 to the power 4. That's the power sum symmetric function polynomial corresponding to that. Then we have 2 terms where we have just 1 4 cycle. So we have 2 times, we have 2 times x1 to the power 4 plus x2 to the power 4 plus x3 to the power 4 plus x4 to the power 4. And then we have 1 term of the form x1 squared plus x2 squared plus x3 squared plus x4 squared whole squared. So that's the expression, and if you simplify it, you'll find that it is it's just let's see, x1 to the power 4 plus x1 cubed x2 plus 2x1 squared x2 squared plus 3x1 squared x2 x3 plus 6x1 x2 x3 x4 plus, now this whole thing has to be a symmetric polynomial, and what I'm saying is that once you write down the coefficients of these monomials, all the other monomials that appear with their coefficients will be inferred from this. So for example, x2 to the power 4 will also have coefficient 1, x3 squared, x4 squared will also have coefficient 2, and so on. So what I mean, plus symmetric terms. So add what you need to make this a symmetric polynomial. So in particular, what this is saying is that the number of, let's just look at this term over here. Okay, the number of necklaces with 2 beads of color 1, 1 bead of color 2, and 1 bead of color 3, and what I mean is equivalence classes of necklaces. But okay, a necklace is an equivalence class, maybe let's just say it like that, is 3. You can try to draw these and check that what I said is right. This term here, the 6, x1, x2, x3, x4 says that if you want the number of inequivalent necklaces with 1 bead of each color, then there are actually 6 of them. Again, try to list all of them. So that is the Polya enumeration theorem.